Yeah. So
What's up?
when we're, I noticed that a lot of times it's mostly just been integers. When we're initializing something, we just say like int x is equal to 5 or something. So when we're calling it like if in higher level code, if we were to say a double, we would then use 8 bytes, right?
Sorry,
Because
you cut out a bit there. Could you say that one more time?
oh, sorry. I was asking about how would it look like when we're like using different data types, and that the only thing that really changes is how many bytes there is, right?
Um, yeah, and also the way that the way that the processor interprets the values. So, for example, a double or even a float, right? A 32-bit float versus a 32-bit int. While they're the same byte length, they have the same number of bits in each of them. The way that the value is encoded is different between the two. You'll get a little bit into that in CPE 300, but let's see if I can get it out. So in a floating point value, you actually express stuff in sign magnitude form. So it looks like this. I think it's So in the typical two's complement form, the way that we have integers stored, we have the topmost bit represents the sign, but it's also a value because we have 2 to the, so negative 2 to the n, and then we have 2 to the n minus 1, 2 to the n minus 2, dot, 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 2 to the 1, 2 to the, where this is bit position 0, this is bit position 1, dot, 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 this is bit position 2 to the n minus 1, n minus 2, and say if this was a 32-bit value, then here n would be 31, n minus 1 would be 30, 29, dot, 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 1, 0. So the way we store it in terms of integers, like I mentioned, is in two's complement form, where this top bit not only represents the sign but also has a magnitude associated with it. It has a value. Here it's 2 to some power. Whereas if we're expressing it in sign magnitude form, the top bit just represents the sign, and the rest of the bits represents the actual magnitude of your value. And so in floating point, you have 8 bits to represent your exponent, and then you have 23 bits to represent your significand, also called the mantissa, also known as the fractional portion, the number part. So the way that this is typically expressed is, I guess you could say, so this fancy notation just indicates that your sign tells you whether or not it's positive or negative. If this bit is a 0, it's positive. If this bit is a 1, it's a negative. This is just a mathematical way of notating that, but that's all that means. Here, your exponent represents basically which bit position you're in terms of orders of magnitude. So if your exponent was, say, 7, that means that whatever your fraction was, you do that times 2 to the 7. So you shift it over by 7 binary points, or 7 binary spaces. My stuff is lagging. That's fine. And then your significand is the, like, if you're writing it in scientific form, that's like the fractional part that's left over. There's a few extra details. Specifically, this significand isn't actually correct. The way that you would actually write this, accounting for the fact that they do two things in particular to the way that they encode this that's different from what you might think. I'm just going to write sig instead of significant. So they actually do what's called biasing to the exponent. So when you have a float, the exponent can range between minus 127 and 120. I think it's minus 127 and 127 because it's 8 bits. So that's your range that you have. Yeah, that sounds right. So minus 127 to 127. But they actually bias it. So when they encode the value, instead of writing it in 2's complement as the number, they actually write it in just straight binary, no 2's complement, with that number added with 127. So if they wanted to represent the exponent of 2, they would say 2 plus 127 is 129, and then they would write that in binary, no 2's complement. And then that's what they would encode here. And so that's why you have this unbiasing of the exponent, because when they store the value in data or in a register, they bias it by adding 127, so you have to subtract that off when you do actual calculations to figure out what the value is. And then for the significand, they actually normalize the number. So you know how in scientific notation, you write stuff always as something like this. So you always have exactly one digit here in the front of your scientific notation, and then every other digit is just written as part of the decimal point. It's actually written in the same thing here, but what you can do is you can say, well, in decimal, there's only 2 options. In decimal, there's 10 options. You can have anything being in here from 0 to 9. But in binary, there's only 2, right? You could have something like this, or you could have something like this. And so what they do is they always normalize the number such that if there was zeros leading zeros, they move the decimal point over and over and over again until they hit a 1. So this one can be expressed as 1.0 times 2 to the minus 2. All I did was I shifted the decimal point to make the number 2 times, shift the decimal point to make it 2 orders of magnitude bigger, so I have to make it 2 orders of magnitude smaller in my exponent term. And so that's actually what they do. They normalize it, so the most significant bit is always a 1. But since it's always a 1, they actually don't need to put that in the encoding. So in the encoding, they don't encode the 1, they encode everything after the 1, which is why I write 1 plus the significand, because this is just the stuff after the decimal point. The 1 here is implied in the actual encoding. It's not encoded as part of the number, but it's known that when you actually go to calculate stuff with it, that is always a 1. Okay, now I know I went kind of into it with lots of details and not a whole lot of... I went through it pretty quickly, so it's fine if you didn't understand that much of it. Basically, the gist of what I'm trying to get at is the way that we encode the integer numbers and the way that we encode floats are really different. And so while they might be the same byte size, the way that the processor treats the number are different. They have different paths, basically, to calculate the same thing. You have to have a floating point unit in your processor, which is dedicated to specifically calculating floating point calculations. Okay. So I know I went off a little bit on that. Did you have any questions?
I think I'm good. Just a lot of process, a lot to take in, but
I mean, you don't really have to remember all of this stuff. The main takeaway here is we encode it differently from an int, and because it's encoded differently, we have to do calculations differently. So we need different processor hardware to do the calculations. even though it's the same byte size, the way we use those bytes and the way that we encode our number in those bytes are different. So we treat it differently. That's the main takeaway. The main reason why I actually went through this was just to show you how different they are. By throwing all this mess at you, you're like, wow, that is way different than anything that I would be doing for like a regular int. And it is really different. This is the IEEE 754 single precision floating point encoding standard. There's also encoding standards for double precision, which are doubles in C code, where it's 64 bits wide. You still have a single sign bit. You have 11 bits for your exponent, and then the rest of your 52 bits. The rest of your 52 bits are for the mantissa, the significant or the fractional portion. And the same rules apply. Exactly what I mentioned here. The only difference is that your ranges have changed a little bit. And then there's also quad precision, which has some encoding I can't be bothered to remember. But they are very different from your standard integer encodings.
Okay, thank you.
Yep. You got any questions for me, Shauna? Did your Venus stuff
I
work?
do. It didn't work. No.
Okay, fair enough.
So, yeah, I'm just off by like literally one line. So I've been trying to like get this to work for 45 minutes for the last question, the for loop, of the homework.
Let's see the very last question.
Yeah, it's the for loop.
Okay, I'm gonna go ahead and erase this stuff about floating point. So that for loop. So I'm gonna go ahead and write it up on the board really quickly. Okay. So what
And
I'm gonna
it's-
do. What's that?
Oh, sorry. No, I was just gonna say like my memory is incrementing, my I is incrementing, my escape is incrementing. Like when I get to I doesn't equal 10, it's really just the vals I equals I. Like for some reason that register is not taking the I value for me.
Okay, so let's just look at how we're supposed to write this. And I'm gonna go ahead and write down a few notes. So the first note is the base address. The base address is in register S5. And I believe the base address they wanted to be hex 230. Yes. And then we'll go ahead and say that it doesn't mention where I is supposed to be stored. At least I don't see that it does.
Yeah.
Oh, no, it does, actually, in the beginning of question 3.
Yeah, it's S1, right?
Yep. And then that's the only other thing I care about. Okay, so S1 and S5 are going to be our I and base address. So I'll just focus on writing the code for this inside of the for loop, and the rest of it shouldn't be too bad. So I'll just focus on that inside. So kind of going back to how we talked about it on Friday, what are we doing here with this line of code? What is it actually doing?
So for that one, I'm imagining it's writing the data from I, which is register S1, into what we're going to have for Val's I, which I made like a temporary T2.
Yeah, so we're writing to somewhere in memory. Specifically, we're storing to memory, so we're going to be using the store mnemonic. We're going to be saying store word in this case.
Oh my gosh,
And-
really?
Yes.
Okay, I was using load word. That might be where
Yeah, that
where
would
my
do.
line is.
Right, because loading
Okay.
means you're taking a value from the memory and you're putting it into one of your registers. Storing is taking something from your register and putting it into memory. And that's what you're doing here. You're taking something from a register and putting it into memory.
Wait,
you would do
I think
stores.
I think I'm getting confused again with these words. So like,
It's
because
very
I
easy
was
to get
thinking,
confused, yeah.
yeah, I was thinking I was gonna load the I into my temporary register T2, which T2 had the val I. What? Oh gosh. Store, like, aren't I reading the memory from I into val I?
Okay, so you're reading the value of I into memory. You're storing it into memory, right?
That's what I thought, right?
Yeah, that's correct. And so whatever I is, it could be 0, it could be 1, it could be 2, it could be 3, up to 10. No matter what those values are, that's what it is. And that's what you expect to be stored if you look at the number in decimal in memory at those locations. You expect it to say 0, 1, 2, 3, 4, etc.
Right.
in decimal.
Mm-hmm.
So, there are a few ways you can go about it. What I'm going to do for the moment is I'm going to use a temporary register to represent my offset from my base address. So I'm going to do T1. T1 is going to be the register which is going to store my offset. So what I'm going to do is I'm going to say I'm going to take T1 and store something into it. Or I'm going to put something into it. Now the value that I want is going to be the offset from my base address. Well, the offset, if you recall from our discussion last time, is I, but multiplied by 4. Because remember that the way we store these arrays is that the first index, so the first index is our base address. So in this case, it's hex 320. But remember that when we go up in memory, because RISC-V is byte addressable, we go up in 4s. So the next term is going to be hex 324, and then hex 328, and then hex 32C, and then hex 330, and so on. So this is where address 0 is. This is where address 1 is. This is where address 2 is, and 3 and 4. In general, for any offset, you just take that offset times 4, and that's the actual offset in terms of addresses. So the offset here is 0 times 4 equals 0. So it's 0 away from 320, which is correct. Here the offset is 1 times 4, which is 4. So that's saying that 324 should be 4 units away in addresses from 320, which it is. Again, here, 2 is the offset, 2 by 4 is 8. And so we say, okay, well, 328 is 8 away from 320. And indeed, that's correct, and it continues. So what we do is we have to take the index and actually multiply it by 4, and that's the offset. So I'm going to do that same thing here, except remember that I can, instead of doing a multiply instruction, I can do a shift instruction if I'm multiplying by a power of 2. Here I need to shift to the left twice, because that's the same thing as multiplying by 4. Just like how in decimal, if you move the decimal point, so if you move the decimal point to the right, which is the same as shifting the number to the left, if you move it once, you multiply by 10. If you move it twice, you multiply it by 10 squared, 10 cubed, 10 to the 4th. Same thing with shifts in binary, except since it's not base 10, it's not 10 to the power of something, it's base 2, so it's 2 to the power of something. 2 to the power of how many shifts you have. So here, to get 4, we need 2 to the power of 2, or in other words, 2 shifts. So I say shift logical left immediate. So shift, and I'm doing a logical shift, so I'm not doing a sign extend, I'm doing a 0 extend. And then left, so I'm shifting everything left by an immediate value. and then I'm going to store it in T1. So I'm storing my result in T1. The thing that I'm going to be shifting is going to be whatever I was, and I in this case is S1. And I'm shifting it by 2 units, so I'm shifting it twice to the left. And so now on this line, T1 is going to be my offset. So now that T1 is my offset, I'm going to actually add it to the base address to get the full address. So I'm taking whatever was in T1 previously, the offset, plus the base address, and the base address plus the offset is the full address, and that's being stored in T1. So now T1 holds the full address. And then all I need to do is write to the memory location at that address. And so the way that, again, I write to memory is I say store word, or you could do half or byte, depending on the size of your information. I'm storing, and then the information I'm storing is I, and I is held in S1. So this is the information I'm storing. And the place I'm storing it to is the address, which here, remember that T1 was my full address. So I just put a 0 offset from there, because this already is the entire address. So what this is going to do is it's going to say, well, the memory at the address of the value of T1, so I'll say T1. So the memory at address T1 plus 0, the 0 there is because of the offset of 0, receives the value of whatever was stored in S1. Here, remember, S1 is I. So the data in S1 is being stored in memory at address T1. And remember, T1 is the offset, which is 4 times I, plus the base address, which was stored in S5. And that is the entire set of code to represent that inside. We have figured out what our offset was, found our full address that we're writing to, and then we wrote to that address. That entire set of code is what's inside the for loop, and the rest of the entire set of code is just how do you do a for loop, how do you do just how do you do a for loop, how do you do these increments and the comparison and the initialization and stuff. But that's mostly about making a for loop, not the internal stuff. With that in mind, were you able to get it to work in Venus? Was it just your loads?
Yeah, I'm pretty sure. I'm going to run it one more time now that you're done speaking. But yeah, I had LW S5, comma 0 T1. And it was just a mess.
Yes, that does sound like a little bit
because I
of a
was,
mess, right?
yeah, I was like flipping the 2 and I was using load word.
Yeah, so you
I
were
get
loading
those
stuff into
really-
you were loading stuff into where the base address should have been,
Yeah.
and then you were loading, right? Yep.
Oh,
Okay. Well, hopefully that
gosh.
does fix
Okay.
it. So I'll let you go and run it.
Yeah, thank you.
yeah.
Be right back.
Okay. Did you have any questions for me, Good Noodle?
No, I was just thinking about like how that one line just has like three lines in assembly.
Yep.
Hmm.
There are lots of lines like that. You can write some pretty long lines in C code, and it takes you a little while to do them. Like, let me think. Right, this is the distance formula. And I wrote it in one line of C code, but I'm sure you can imagine that there's quite a bit of going on here in assembly.
Yeah.
1, 2, 3 function calls, and then you have to initialize your x and the y, and then you need to initialize registers to be the value of 2, because when you do a function call, you have to have all of the arguments in registers, and then you have to take those return values and then plug them into other registers and then feed them into the other function calls, and then do that again and plug it into this function call and then read it again. And there's, it'd be at least 10 lines of, well, I'd say around probably 10 lines of assembly just for this one line, which is fairly understandable mathematically, but probably pretty annoying to do in assembly. And that does happen pretty often. Especially when you have high level, like really high level code. Because C is actually one of the lower level sets of code. Do something in Python, you can do a lot in one small line.
But isn't Python ran on an interpreter rather than getting compiled?
Yep.
I believe. Yeah.
That's right.
But it would still be interpreted as a machine, as assembly language or machine
Everything
code.
eventually has to go down to machine code.
Mm-hmm.
Otherwise, you can't execute it if it's not in machine code. It's just not physically possible. The machine code may differ from machine to machine. I think I've heard of some machines which have hardware specifically designed for particular languages like Java. I may be wrong about that.
Like the Java
Bytecodes.
virtual machine?
Not the virtual, like literal, like an embedded system. I think one of my professors brought up an embedded system that can compile Java bytecodes like directly and execute them directly instead of turning them into, x86 instructions or RISC instructions or something. But regardless, in general, you always have to turn whatever your code is. Eventually, it's going to turn into machine code as instructions that can be run on your hardware. Any other questions for me?
So really quickly, should T1 in our board example get 0, 1, 2, 3, 4, or should get the memory address of where I is?
On which line of code?
On the third one, SW.
What should T1 be on this third line?
Yes, what is T1 after?
Well, remember that
It
this
should
line
be-
doesn't change T1 at all. It just uses T1 as an operand, but it doesn't change T1 at all. This is the line that, the most recent line that actually changes T1. And all this is going to do is it's going to say that T1 is going to be equal to hex 320 plus 4 times I. So T1 should always hold that value after this line executes.
Okay, so that is what my Venus was doing. But now I'm like, okay, so val, in this example, val I is our like hex 230, 234, 238.
This and what I wrote here are the same thing. The only difference is that when I'm writing this, I can kind of imply two things. I can either mean the address of this thing or the data stored at this thing. The data stored at this address. Here I'm saying vals at index I corresponds to the address hex 320 plus 4 times I. The data in there, I don't know what it is until I assign it to I.
Okay. Okay.
Any other questions? Are you guys good if I erase this from the board?
Yep.
Yeah, I think so. Did you go over a little bit more of jump and link? I believe that's what the professor did.
Yeah,
And jump
JAL
register?
and JR. Yeah, sure. Okay. Now, before I write anything, I want you to try and explain to me what those instructions do. Or what you think they do. It's alright to be wrong.
Okay, so if I remember the jump and link instruction, it would be like to jump through a function call, right?
Correct. You can use it to jump to a function call. In fact, that's
function-
a very
oh, okay.
common use for it.
Okay, and then I guess maybe the linking part is. I actually don't know what the linking part does.
So here's what happens when you do a function call. In high-level code, you do a function call, it jumps to the function, executes the function, and then returns to its caller. But in assembly, you have to be able to return properly. Because when you do a jump and link, two things actually happen. The first thing that happens is that you actually store where you are at current, or where you're going to return to. So whatever line you're on, say this is at program memory hex 400. Say this is where your JAL instruction is. And I'll say it says, I'm going to jump to, what do I want to do? Well, I'll write that after later. So here's what's going to happen. I'm going to jump to a specific place in memory, but I also need to remember where it is that I need to come back to. Because not only do I need to jump to memory to execute my function, I need to jump back in order to return to where I was before the function call. And so the place that I'm going to jump back to is here, the next line after this. So now you may ask, okay, well, how do I remember that? Typically what's done is the instruction, when it's ran, it does those two things. So the first thing it does is it saves this memory location, and it stores it into a register. And the register it stores it into is RA, which is the return address register. If I recall correctly, I want to say that it's register 2. Like, when you look at the list, there's hex 0, hex 1, hex 2. We give them names. So, for example, this register is register called 0. I think this is the stack pointer and this is the global pointer. I may be mistaken. And one of these is RA, which stands for return address. And so just as a standard, that register is what's used to store your return address. And so what I can write here is I can just say JAL, and then I can say where it is that I'm jumping to. So if I'm doing a function call to a, I don't know, like a matrix multiplier or something, I can say that's the label that I'm jumping to. And so when I execute this instruction, it does those two things. It remembers where I am going to be when I return, which is on line hex 404, and it stores that in the return address. And then after that, it goes ahead and actually jumps me to this address. I said those two things as if they happen sequentially. Actually, they don't. They happen in parallel in one full execution of an instruction. But both of them do happen. So again, You jump to the place you're going to go, but you also remember where you're going to come back when you finish. Okay. All right, so any questions about jump and link?
And sorry, it remembers through RA, right?
Pardon?
It remembers where it needs to go back to by RA.
Yes,
The return
RA
address? Oh.
is just a number. It's just a name of one of the registers. I don't remember which one. I think it's hex 3. I can't remember. Like, for example, hex 0 is called 0. One of them is SP for stack pointer. One of them is GP for global pointer. One of them, a bunch of them are T0, T1, T2, so on, so on, so on. And so you call this RA. And that's the return address register. And so this is just a function call. That's the entire purpose of using the JAL. You use it and you basically implement a function call. Okay. So now the next instruction you were asking me about was JR. Is that right?
Yes.
Okay, so here's what I'm going to do. I'm going to say hex 534. I'll just make it easier for me. Label. And then, do some stuff. And then maybe down here, hex 554. You say JR. And I'm going to return to the address given to me by RA. So I'd say JRR. So we mentioned up here that when we just write this, code, it stores the return address in RA. So that's actually the part that's link. So remember JAL stands for jump and link. Those are the two parts that I was talking about earlier. You jump to the new place that you're going to be the new function you're calling, and you link to the place you're going to return to. And the link is stored in RA, the register RA, which I looked up and looks like I was wrong. It's in hex. It's register 1. That corresponds to RA. Register 0 is 0. And then some others after that. So that's where it gets stored to by default. Just so you know, this is actually a pseudo instruction. It's not the full instruction. The full instruction actually looks like this. So I said by default, this is RA, and that is true. If you didn't put anything here, it would actually default to RA. But that's the pseudo instruction. The real instruction has some register here. And that's the register you're going to store your return address to. Again, by default, it's RA. And if you don't put anything here, the pseudo instruction is going to store to RA. But this allows you the flexibility to have it store the return address wherever you want. It doesn't have to be in the register that's dedicated for that purpose. It can be anywhere. So typically, whenever we're doing function calls, we actually just use the pseudo instruction and write this. Now the next instruction here, JRRA, this is my return. So in C code, when I say return, this is effectively what I'm calling. I'm calling this function. And so I'm going to jump to a register. And the register that I'm jumping to is RA. And when I say jumping to, I mean I'm going to look in that register, see what the address is in that register, and I'm going to jump to that location in program memory. So in here, I said, oh, well, hey, right before I called my function, or during my function call, I stored hex 404 in my register RA. So after this line executed, RA holds that value. But then on this line, I said, okay, I'm going to jump to wherever RA tells me to jump. Well, since RA still has 404 in its register value, this is going to jump me to location 404. So that's the basics of it. This is a call, and this is your return. And the way that you remember how to return is you have an extra register just to store the place you're going to be returning to. So you remember where that is on the JAL instruction. You store that return address on the JAL instruction, and then you use that return address on the JR instruction. Okay. All right. Any questions?
When you use JR, it doesn't have to just be RA, right? It could be any.
It can be any, yeah. So let's say that you didn't do the pseudo instruction and you said, I want to store it in T0. Then you could totally put T0 here. And then that would work. However, there is a reason why we use RA. And it's the same reason, in fact, why we have different names for the registers. So I'm sure you guys have noticed. You have T registers, S registers, A registers. Do you guys remember what those letters stand for?
T is for temporary.
Yep. What's S stand for? Stands for saved register. What does A stand for?
That was argument.
Yes, argument registers. So the standard is you use the A registers to be arguments for function calls. You use S registers if you don't want function calls to mess up something in that register, because when you do a function call, in that function, it's going to use registers. So if it uses an S register, it has to restore that value that was in there before the function call in order for the main function to call to the function to retain whatever was in the stored register, S0 or S1 or S2. So generally speaking, whenever you're using an S register, that is what you call call E saved. So call E is the function that you're calling, and it has to save a register value on the stack before it's allowed to use it. So it has to save a bunch of values, and then it can use that register and then restore it right before it returns. So that's why it's called saved. And then temporary registers are what's called call-er saved, which is to say that if my function calls another function, and that and I'm using something actively in register T0, I have to save T0. I can't expect the caller, the function that I'm calling, I can't expect him to save it for me because it's a temporary register. He can do whatever he wants with it. And so that's just standard practice that's followed when you code in RISC-V. Similarly, it's standard practice in RISC-V to use RA to store your return address and to not use it for anything else. Oh, yeah, one other note. This is actually also a pseudo instruction. So I mentioned that JAL is a pseudo instruction. JR is a pseudo instruction. It doesn't stand for JR. It stands for JAL. So JALR stands for Jump and Link Register. Given you know what Jump and Link stands for, can you guess what Jump and Link Register does?
I would think that it would jump back, but the thing is that it says and link registers. Like,
Yeah, that's what the ALR stands for. Jump and Link Register.
so is it linking back to RA?
Let me go ahead and write out a little bit more of what this does. So jump and link register looks kind of like a store word instruction almost, or like a load word instruction. You have the first register, whatever it is. I'll call it RD. And then you have it followed by some immediate value outside of some register value in parentheses. So it actually looks very similar to a load word. So here's what this does. You're going to be taking this value here, this immediate plus RS, and what you're going to be doing with it is that is where you're going to be jumping. So here, if this instruction was translated, this pseudo instruction was translated into its non-pseudo instruction or correct instruction counterpart, it would look like this. That's what it would look like. So that second bit basically just tells you where to jump in program memory. So that's going to tell you where to return to. Okay. Now, can you guess what this part's going to do? Because here I put the 0 register. I could actually put something else here. Could you guess what that's doing?
I think it may be has something to do with the ALR part.
It does, yeah.
And
So we
link
did the
re-
jump
okay.
part here. So this is the
Mm-hmm.
LR part, the link register. So what it's going to do is it's going to store, just like here for JAL, it's going to store the next address after it as a return address. That's what it's going to do. Just like in JAL. And so it may be like, it may come to you, why would I need both? Why does this copy the functionality of that? The interesting part, though, is that they aren't quite the same. So jump and link just has that offset value. It just has an immediate here. That label is encoded as an immediate. Whereas JALR has an immediate plus a register value. So JALR can jump to, well, whatever's in here. Any immediate, what's it called? Anything in this register plus some immediate value. So it can jump really far. For JAL, the immediate encoding is not 32 bits. It's something like, oh shoot, what is it? Something like 17 bits, I think. So not that big. Whereas here, the address to jump to you can specify could be 32 bits. So you have a huge range you can jump to, whereas this is not a huge range. And the second detail is that this is a relative address. So the way that the label is encoded is it's not encoded as the absolute address here. So label, this immediate, does not hold the value hex 534. It actually holds the difference between these two. So it holds the difference between 534 and where you're going to be returning to. So it'd be the difference of these two, which would be hex 130. That's the immediate that's encoded here. It's a relative address. So from how far is it from where you're at to where you want to go. Whereas this, it's not a relative, it's an absolute address. It's you go to whatever the address is and that's stored in here plus some immediate offset. So those are the two minor differences between these two. Now, you're not really going to be using this jump and link register as an instruction by itself, because most of the time you're going to be using this, the pseudo instruction version of it, where you just return, where you just return to wherever your return address specifies. And I should have erased it, but there we go. but that instruction, JALR, the reason why this was 0 here is because remember, that's where we're storing a return address. But remember that 0, the register 0, is not actually a register. It holds, it's just the wires that are all tied to ground. So effectively, by putting this here, that means we're not storing a return address, which is why this pseudo instruction is decoded into this. Because when you do a JRRA, you're planning to return from a function call. You don't need to save where you were at right now, because you're leaving this function permanently. You don't need to return to it. And if you were going to return to it, then the main function would just call it again, in which case it already has the label and it can deal with it. So here, you're not saving the return address because you're not writing it to any of the registers. You're writing it to register 0, but that doesn't actually change the register. It always holds 0. And so that's why it's a 0 there. These two are the exact same. Okay. So with that out of the way, y'all got any questions for me?
What cases would there be, or if we were to do JLR and then use a different register other than like 0?
So, I mean, all that would do is, like I mentioned, it would behave exactly like JAL. So you'd store this in T0 or something. It would behave exactly like JAL in that you're storing wherever this is right now, the address right after that, you're storing that in T0. So if this was at address 554, then 558, the next address, would be stored into T0. And then the place you're jumping to is going to be whatever this address is. So you asked, like, what the other cases are for the registers you can put here, and you can put whatever register you want. Doesn't matter.
Okay, thank you.
Yep. All right. Again, though, we typically don't use jump and link register as a full instruction. We use its pseudo instruction counterpart just to make our lives easier. And if I recall correctly, there's also a pseudo instruction which is just RET, which is return. You don't type anything else, you just type RET, and it does the same thing as this. Though I think in your classes or in your homeworks, these will be what you will want to write down. These will be like part of the answers. You won't see RET as one of the answers. And similarly, there's also a pseudo instruction for jump and link. And the pseudo instruction, funnily enough, is actually just call. So you'd say call label instead of jump and link label. And so it more closely resembles a function call. But again, you won't see that syntax written in any of your homework solutions or anything. You'll just see it as JL label because it's you want to understand how those instructions are being executed. The point of digging into this assembly is to get past those layers of abstraction and see what's going on, happening on underneath. And so if you just say RET and you just say call, it's not really specific. Whereas if you look at these actual instructions, you can look at the actual binary encoding of those instructions, how it's turned into machine code, and then how it gets run on your processor. Versus if I just say call, that's abstracting a layer away, and then I have to peel back that layer to then see what this is, see the machine code, see how it's run on the processor, etc. Okay, any other questions on that?
No more questions for me. Thank you.
Yep. Got any questions, Shauna?
Nope.
Okay,
I think I'm good.
Okay, we've got another 5 minutes. I didn't tell you guys, but I will not be uploading Friday's office hours because the audio did not get recorded for some reason. So don't expect to see a video up for last Friday. I guess I must have been muted the whole time or something on my OBS. I don't know. Maybe I was muted in Discord too. No one was in Discord, so that's a possibility. What did you guys go over in class today?
Jump and link and functions.
Okay, that makes sense. That's pretty reasonable. So use them mostly for function calls. Jump and link to call a function, and jump return JR followed by an RA to return back to where your function was called from. The line right after where your function was called from. No other questions? Okay. Well, I went over quite a bit today, so don't feel too bad if you didn't get all of it, especially the stuff at the beginning about the floating point encoding stuff. I went over that very quickly and not really explaining it that well. So don't feel too bad if you don't really understand that all. You'll also go over it in 300. And if you guys want, I can, in future office hours, if no one has any other questions, I can dedicate more time to explaining the floating point decimal encodings and whatnot. Same thing goes for the instructions. I went through those relatively quickly, so I'm more than happy to explain them again next office hours if you guys want me to. But basic stuff. JAL calls a function. JRRA returns from that function. That's mostly what you're going to be using it for. Okay, no other questions, right?
Yep, I'm good. Thank you.
Thank you.
Okay, I'll go and end office hours early. Thank you guys for coming, and I'll see you both tomorrow.
See you tomorrow. Thank you.
Have a good night.
You too. Bye.